To extend the Western Heights Road, the Reunion Island authorities laid down a route crossing several ravines through the Piton des Neiges and Piton de la Fournaise volcanic formations. To cross the first of these ravines, the project owner, the consulting engineer, JMI, Cetoroute International, and the architect Alain Amadeo accepted the challenge of building a particularly graceful bridge. It is a flat arch bridge with a span of 280 meters, a record. Bouygues Travaux Publics and DTP Terrassement were chosen to build this bridge. The bridge was designed by the technical department of Bouygues Travaux Publics. It's a composite bridge, cantilevered out from the abutments in a succession of 12-meter long and 12-meter wide segments. The gravity abutments each consist of 3,000 cubic meters of concrete. The 2,600 cubic meters of concrete for the top and bottom flanges of the arch are C60 grade. HPC was previously unheard of on Reunion Island, whose basaltic aggregate does not give concrete good rheological properties. Between the flanges are 84 diagonal steel struts, some of which had to be post-tensioned as part of the construction cycle by a VSL, intra-4 work crew, integrated into the construction team. The erection cycle of a segment breaks down into 9 phases, starting from an initial situation, phase 0, where the concrete of the bottom flange has set. The lower traveling form is backed off and resecured to the concrete, bearing on blocks placed at determined strong points. Phase 2 involves moving the upper form carriers forward. They are suspended from the formwork of the top flange. In this phase, the form carriers are moved 6 meters 70 in a single action and are supported by the lower traveling form by means of a prop. In phase 3, the upper formwork is moved forward 12 meters 70 in one go. The 3 forms are independent. Once they are in position, we fit the diagonal compression struts using the cableway. Phase 4 involves closing the forms, erecting props, placing the reinforcement, and concreting, of course. After the concrete has been placed, Phase 5 begins. This involves clamping the forms to the top flange and releasing the upper form carriers and hanging them from the wheels on the upper form. In Phase 6, we move the upper form carriers forward 6 meters, and then we clamp the outer form carriers to the concrete flange which has just been built. This takes us to Phase 7, where we release the lower traveling form, hang it from the 2 outer members of the upper form carrier, and move it forward 12 meters 70 in one go. Phase 8 involves raising the lower traveling form using double-acting jacks in a series of 65 centimeter strokes. Phase 9 involves clamping the lower traveling form to the concrete of the preceding section of the bottom flange, then placing the reinforcement, fitting the tension diagonals, and concreting the bottom flange. The tools we use are different in each cycle. I mean, the diagonals are much shorter. Their position is different every time, and the top or bottom nodes to which the diagonals are attached vary every time. We're going to release this diagonal, and then we're going to adjust it vertically, axially and laterally, until it's in its theoretical position. And then we'll bring up the reinforcement cage and place it against it. When I'm doing a bottom flange here, Alain is working on the top flange on the other side. In fact, things are organized so the same job isn't being done at the same time in 2 places. It's an exceptional bridge. It's the first time we've worked with pours of 12 meters. In fact, for VSL, the interesting thing is that we haven't got a whole lot of pre-stressing strands in meters, but that the pre-stressing is difficult to get to and difficult to work on. We don't have time to get bored on this project. We have to keep up with the cycle imposed by concreting. Right now, we're in the phase where the bottom flange is suspended from the top flange by the tension diagonal. And we're going to cancel out that tension in the diagonal by post-stressing it with two tendons made up of 19 15mm strands. It takes about 800 tons of pre-stress to cancel out the tension and convert it into compression. The pre-stress can be removed by injecting the tendons with Inject ELF petroleum wax. We inject it from the bottom and it works up to the top of the end cap. The aim is to build a bridge that will have this shape when it gets to here, at the stitch joint. To do this, we build each successive part of the span higher than the design profile, since the weight of each additional segment makes the deck drop a bit. For example, segment number 10 will drop 16 centimeters when it is concreted, and when segment number 11 is concreted, it will have dropped a total of 33 centimeters. To check the shape of the bridge, we have 8 leveling targets on each segment of each flange, which makes about 350 in all. They are surveyed every day, and the results are sent to the design office at Challenger, so they can tell us the level the next segment should be set to. A bridge like this, constructed 10,000 kilometers from Challenger, cannot be designed and built without effective symbiosis between all the divisions of Bouygues TP. The design office in charge of designing it, TPMP, which worked on the construction methods, and the tools to build the superstructure, and the workforce which succeeded in working the technique, safety, and the construction cycle into a particularly tight deadline. Sure, it's a project involving a lot of technology, but it's the experience of the workforce that gave it that little something extra. Stitching the two halves together is the final operation on the bridge. We'll be left with a 1 meter gap between the two sides, and filling that in will be the icing on the cake. We're really looking forward to finishing the bridge because it'll be really something when it's done. Integrating technicity and innovation on a project a long way from our base is a challenge.